So welcome all. So this is the another part of the design of a column. So here we will see a numerical and clear all our doubts. Okay. So see what is been given. Design a short column of size 400 into 550. Okay. So here is the diagram given 400 into 550. Okay. Using M20 grade of concrete and Fe415 steel. The column is subjected to an axial load of 1500 kilonewton under service and as usual condition of live load. The effective length of the column is 3.1 meter. The effective length is given and is braced against side saw in both direction, means rotation is also restrained. Okay, so now we will see what are the steps involved in this designing. Okay, so first what we will do, we will just write the given things. Okay, so see, the first the dimensions are given, that is in the x direction, that is dx is given as 550 mm and dy is given as 400 mm. Okay, we're taking it the dimension like this. Okay, you can take different one also. Now what are the other given things? So the L effective. Okay, so the effective length, see, the L effective is 3.1 meter, or we can convert it into mm, so it will be 3100 mm. Okay, so the other thing that is given is FCK is equal to 20 Newton per mm square, and Fy is also given as 415 Newton per mm square. Okay, so axial load is given, so we can write it as Pu. Axial load is taken as 1500 kilonewton, or we can write it as let it be. So the factored load, we can calculate it now only. The factored load, what is will be the factored load? 1.5 times this load. Okay, so it will come to 2250 kilonewton. Okay, so this is the factored load. Now we will see what we have to do. First it is said that design a short column. Okay, so first we will see if it is a short column or a long column according to the given dimensions and the L effective value. Okay, so we will check the slenderness ratio. The what is slenderness ratio? First we will write. Okay, slenderness ratio, so it is denoted, this slenderness ratio is nothing but the L effective value divided by the least dimension. We have done it earlier also, learned it earlier also. Okay, so now for the slenderness ratio for x direction will be what? See, the L effective value is same, only the least lateral dimension will change. See, we have read earlier that for x direction what we have to do, we will take the value of 550. Okay, so we will take the value as 550. As for the least lateral dimension, it is coming as 5.63, and for y slenderness ratio in y direction, this effective value is same, just we will change the value of the least lateral dimension. It will come to 7.75. See, we know for short column, this slenderness ratio, or we can say that the L effective divided by the least lateral dimension should be less than 12. So see, both these values are less than 12, so hence we can say it as this is a short column. Okay, So we can say it as this is a short column. Okay. So now what we will do, we will go to our next step. That is, we have to calculate the minimum eccentricity. Okay. The next step is minimum eccentricity. So we know the formula for the minimum eccentricity. What is that? So E minimum is equal to 5L naught divided by 500 plus LLD divided by 30. Okay, you can check it once. The minimum eccentricity value what we have written earlier, just see, yeah, see the E minimum is the unsupported land divided by 500 plus LLD 30 or 20 mm. Okay, whichever is maximum. Okay, whichever is maximum. So we will now do it here, this calculation, or see 20 mm, whichever is max. Okay, so let's do E minimum. So E minimum will be calculated for both direction. So we are calculating first for x direction. So the L effective, so the L naught value will be same, that is 3, or L naught or L effective, whatever you tell that, 3100 divided by 500 plus LLD for x direction is 550. Okay, 30. And E minimum for y direction, only this LLD value will change, the other values will be remaining same. Okay, so for y the LLD will be 400, we have seen it previously also. So for this value, if you calculate it, it will be coming to 24.53 mm, and the y direction it will be coming to 19.53 mm. Okay, see the minimum eccentricity value has been taken, but now we have to do the check. So now we have to do the check. So the check is for E minimum. E minimum, what is the check? So the check is that E minimum should be less than 0. Or equal to 0.05 the LLD. Okay, so we will calculate this value now. Okay, so let's see. Yeah, so 0.05 LLD for x direction, that is coming to 0.05 into 550. This is for x direction. This E minimum value should be less than equal to, okay, so if you calculate this, it will be coming to 27.5 mm, and the E minimum, this is for x direction, and this is E minimum for y direction, should be less than equal to 0.05 LLD, that is in y direction, that is coming to 0.05 into 400. So this value will be coming to 20 mm. Just see one thing, that is the x value is coming as 24.53. So it is the here the coming, it is coming as 27. So it is less than that only. So this value, this condition is being satisfied. Okay, so the next thing, in y direction it is coming to 19.53. So here it is 20. So this condition is also, sorry, so this condition is also being, this condition is also being satisfied. Okay, so now we can write that in both the direction the eccentricity value will be considered. So for both directions eccentricity condition satisfy. Okay, so now we will use our formula, that is, now we will calculate column load design. Okay, so what is our aim for calculating here? So mainly our aim is to calculate the area of steel. So our aim here is to calculate the area of steel, AS, okay, or AST, whatever you can write. Okay, so the formula here is PU is equal to 0.4 FCK AC plus 0.67 FYAS. Here AC is the area of concrete, that is, we can write it here AG minus AS is equal to AC. Okay, so previously we have seen it, so we will now put it in the formula. PU is equal to 0.4 FCK AG minus AS, okay, plus 0.67 FYAS. So AG is equal to B into D. So here B is 550 into D is 400. Okay, it comes to 221. So this value is coming. Okay, so PU, see, we have calculated the PU, the factored load here at the starting only. See, this is the PU value 2250. Okay, so kilonewton, we will convert it into Newton. So 2250 into 10 to the power 3. Okay, so now we will write this side is equal to 0.4 FCK, so it is 20. So AG value we have got 2121234 minus AS, okay, plus 0.67 FY is 415 AS. Okay, so now we will calculate it. This side is coming to 17634 minus 8 AS plus 278 AS. So this side is 2250 into 10 to the power 3. So again 2250 10 to the power 3. So it's coming to 1764 plus 270 AS. So from here AS is coming to 1815 mm square. Okay, so the area of steel is coming to 1815. Okay, so we have seen previously what we have to do. After that, we have to assume a dia. Okay, we have to assume a dia of a bar. Okay, so we are assuming as, see, as the area, if we know, we are acquainted with the area of bar of a 20 mm and 16 mm, we can see it here that here the area is more. Okay, so the required area of steel is a more amount. So we are assuming that we are providing, providing 4 number of 16 dia bar and 4 number of 20 dia bar. Okay, if we calculate it, this summing up Okay, the area of steel will be coming to 2060.9 mm square. Okay, so this is as provided. Okay, so this is as provided, and this is the as required. Okay, so the as provided is greater than as required, so we can provide it. Okay, so now you can do here this permutation combination also. If you get that, if you are thinking that how this value is coming, so you can just calculate on your own that this 4 into pi by 4 into 16 square plus 4 into pi by 4 into 20 square. So this, if you do this calculation, it will coming up to 2060.9 mm square. So this is the as. Okay, so now we will calculate the number of bar. Okay, so we will calculate the number of bar required. So how we will so this is the area. Okay, we number of bar, so we have gone it. We will now calculate, sorry, we will now calculate the maximum area of steel and the minimum area of steel. So what we know, so check, you can write it here, check for max and minimum area of reinforcement, okay. So we know that the for minimum it is 0.8% of cross section area. Okay, cross section area, and max is 6% of cross section area. Okay, so see, we have to calculate that what it is coming. So the percentage of reinforcement provided is very simple. Just take the total area of steel provided into 100 BD. Okay, BD. Okay, so if you calculate it, it will be coming up to 0.937%. So it is greater than 0.8 and it is less than 6%. So it's okay, we can provide it. This area of steel is okay. Okay, so next step, what is that? We have to design our lateral ties. Okay, or the transverse reinforcement, our transverse reinforcement. Okay, so first we have to fix the dia, and then we have to fix our spacing. So dia of lateral ties or transverse, anything. Okay, anything we can tell. So dia of lateral ties is equal to phi of main bar divided by 4 or 6 mm, whichever is maximum. Okay, so if you do this, that phi of main bar, that is 20 by 4, is coming to 5 mm, and 6 mm, so whichever is maximum, so we will take the die as 6 mm. Okay, now we have to calculate the spacing. So spacing according to IS 456, so the spacing will be the least lateral dimension or the 16 times the dia. Okay, or 300 mm, whichever. So, once we can check it, we are doing right or wrong. Wait a minute. Yeah, see, the spacing is the LLD 16 of main dia and 300. Okay, So here our main dia is mainly 20 we will take. Okay, the least lateral dimension is 550 and 400, so the least one is 400. Okay, so if you do this 16 into 20, and here it is 300 only. Okay, so it's coming to 320 mm, and this is also mm, and this will be the minimum of these three, so we can provide as 300 mm spacing, center to center spacing, okay, of lateral ties. So now we will do our detailing. Okay, so previously we have seen that we have to do the detailing. Okay, so let's see. Okay, let's say this is our column cross section. Okay, so we are taking a small here inside this, so this is our red color is our lateral ties. Okay, so this red color is our lateral ties. Okay, so now here what we will do, we will draw our columns. Okay, so see, for what columns we have, 4 of 20 dia and 4 of 16 dia. So one thing you will always remember, that the big dia are given at the ends. The bigger dia is given at the ends. Okay, so these are 20 dia bars. Okay, now we will provide the 16 dia bars here. Okay, so these are the 16 dia bars. Okay, so this is the 550 dimension and this is the 400 dimension. Okay, so let's see. uh, this is our lateral ties, that is of 6 dia ties and 300 center to center spacing. Okay, so the 20 dia, phone number of 20 dia bar, and this is phone number of 16 dia bar. Okay, so our reinforcement detailing is completed of a column. So this is the detailing of reinforcement of a rectangular short column. Okay, okay, so thank you, we are just ending up the lecture here. Thank you, see you back.